everybody. So I have a question. PostGIS or PostGIS? PostGIS, raise your hands. PostGIS, raise your hands. What does Paul Ramsey tell us? I don't know. Yeah. Before I start with the show, I'm going to shift to the demo because it takes a while for the thing to load up. But I do want to prove that this is actually happening. So I'm in RStudio, and I'm just going to tap Run App, and it should open up a window. And after a few moments, it should start loading stuff up. So this is loading. I'm going to go to the presentation now. I'm going to talk today about reviewing some couple GPS and accelerometry data with a project that I built using R-Shiny and various open source packages. I'm here representing myself and the two people that are really the PIs on the project. One, Christy Bjornson at UW and Noel Moreau at Louisiana State University. I'll give an introduction, rationale, measurement and data framework, the mapping applications, and then a live demonstration. So this project is focused on kids that have cerebral palsy. And for those of you that don't know, these are movement disorders that appear in early childhood. Typically, they're caused by abnormal conditions during birth or during pregnancy or shortly after birth. And they occur approximately 2.1 times from every 1,000 live births in the US. And this disorder affects the well-being of individuals and families. There are various treatments for CP, including orthotics. So you see sometimes kids or adults wearing leg braces, ankle braces, using crutches. It's typically hard for them to walk. There's also physical therapy and medications that are used to treat CP. When people are treated for CP, there's always a question of how the therapy helped or didn't help. And so some of the measurements are kinesiology, where they look at gait, stride rates, stride length, posture. And these kinds of measurements are typically done in clinical settings. There's a whole framework for understanding disabilities and how people with disabilities function in society. That's the International Classification of Functioning, Disability, and Health, also known as the ICF. And one of the key concepts in the ICF is this idea of participation in activities of daily life. So if you turn the clock back about 50 years, you would rarely see people that have pretty heavy disabilities in society. They were institutionalized. And a lot of work has been done to make environments more amenable to people with disabilities just being part of with the rest of us. So it's really this participation in life situations that's really key to this ICF framework. Now the question is, how can these clinical observations, we're measuring gait, posture, and so forth in a really controlled setting, and these things are very easy to measure, right? It's easy to measure in a clinical setting, but how do those things translate to real lived experience? And those things, as it turns out, are very difficult to measure. So there was this need for a research framework for assessing important factors in participation. And in this case, it was really walking. So we wanted objective methods for measuring walking and time spent in different settings in the daily life. The research question really is, does an experimental training program lead to better outcomes than care as usual? And there are a couple different ways to measure the outcomes. So there are these typical clinical measurements that I talked about, then self-reported measurements of participation, satisfaction, engagement, and then these objective measurements that we use. So we were looking at steps per day, overall steps per day, and also steps in different intensity strata, and then time spent walking per day, again in different intensity strata, and then steps and time per day spent in different locations stratifying into home and community locations. We'll get into the measurement and data, which is probably more interesting to this group. There were 2 sites, one in Seattle with Seattle Children's and the other one in New Orleans with Louisiana State University. There are about 60 subjects aged 6 to 10 years old. And these are people that had previously been treated for CP at one of the 2 clinics. The 2 treatments were randomized. The TLTT is a typical strength training, and the experimental one is called short burst locomotor treadmill training. And this is the experimental training, which is trying to build not only strength but also power. So the way to think about the difference between strength and power is strength, you could imagine like doing a leg press, right? And that's a kind of a, requires muscle strength. But power would be something like getting up out of a chair, where you need this initial burst of a lot of energy to get started. And the theory is that increasing power and strength is much more effective in the long run for treating people with CP. There were 4 measurement waves, so the first measurement wave before any of the treatments, and then 3 measurement waves after that initial wave. The clinical kinesiology measurements, in this case, were pretty simple. It was just walking speed. Self-selected walking speed at whatever your typical speed is, and then asking them to walk as fast as they could. And this was done in a movement lab. They also measured quadriceps strength, and then for the part that I got involved in, there's a thing called the StepWatch accelerometer, which is kind of a gold standard walking measurement. It kind of looks like people have to wear GPS if they're incarcerated or whatever. Looks like that, right? So it's kind of funny to wear, but I mean, it measures every step. It's really amazing. And it measures and tallies up the number of steps in every 1-minute epoch over the entire measurement period. So when it's not worn at night, it's just going to have a bunch of data that are all zeros. And then we also have them wear a GPS receiver and data logger, and those were recording at 15 seconds. So they were wearing, the kids with leg braces were on one leg they had the StepWatch, and on the other one they had the GPS unit. So I imagine they were really popular at school. Well, that doesn't look the way it should. This is the StepWatch data, and it's basically a big table. It's recording every minute. And the first record includes some metadata, and then we convert that to UTC. What you would see here in the red box is a bunch of timestamps. Those are 1-minute timestamps. And then in the second little red, or in the red box, you have the timestamp and the number of steps in that minute. And so this is measured over a week. Oh, here we go. So those are the timestamps and the number of steps per minute. And then the GPS data, typical GPS data that includes UTC date and time, and then latitude and longitude. So it's pretty easy to take these data into whatever kind of data analysis package you're going to use, whether it's Python or R or Excel or, in my case, PostGIS. So I do a bunch of pre-processing with R. Lots of files. They've got to get manhandled in different ways. And ultimately, they do get pushed into a PostGIS database where the StepWatch and GPS data are joined based on the common timestamp. And so the StepWatch data is measuring continuously, but as probably a lot of you know about GPS, a lot of times you lose signal. So the StepWatch is only going to have a location when there was a simultaneous GPS signal. I put these into a database with partition tables because of the nested structure of subject, wave, and then overall data set. So ultimately what this did is gave us the walking data, but for those records that had a GPS, those walking points were spatialized. Here's a little example showing graphically what I was talking about, is we just basically take these different data sets and put them into a single database where you now have one table that includes all the walking data and geometry fields from PostGIS. The analytic data set is a minute-by-minute set of data that includes the count of steps, the intensity of walking into these 4 different bins, and then when we had GPS, the location. And again, those were stratified into home, being within 50 meters of the geocoded home location, and community of beyond 15 meters of the geocoded home location. So one of the reasons that I was involved is that they always complained about not knowing whether some days of data were valid or not. So imagine days of data where there was just a short period of time wearing the devices, or if they had taken a flight, say going from New Orleans up to visit their grandmother in Chicago. And the researchers that I was working with, they typically only looked at the StepWatch data. And so looking at steps, it was impossible to know if some of these days were unusual in terms of travel. So we wanted to be able to look at unusual travel days. We needed to look at every single day. We had to show the GPS locations and the home location. And this also had to be HIPAA compliant. So there was no way we could put these like on a web map, even, I think there was a restriction against even having it on a closed site on the internet. So everything had to be local. The first application was just, give us a map of every day of the GPS data. And so I created a bunch of maps using Shiny in R, and using Leaflet, not Shiny, Leaflet in R. And you can basically generate a map. And if you've generated a map that you can see in your graphical window in R, you can save that as a PNG or PDF file with this mapshot function. Pretty easy to deal with. You just write the first map and then you loop for selecting the data, and at each loop you pull in new data and make a snapshot. Problem was these were not interactive at all. They only showed the locations. Lots of files were generated. It took, I think, a couple hours to generate the full set of images for every single subject day. Took up a lot of disk space, but people don't worry about disk space anymore. The biggest problem was not easy to navigate files. So imagine a folder full of thousands and thousands of image files. Even though they're named by subject and date, it just became impossible to deal with. And then any change in the design required generating a whole new set of maps, and I had to do that 5 or 6 times. So the Shiny version is an interactive framework. It lets the researchers select specific subjects and specific waves and specific days, and then it generates an interactive leaflet map. So it's not just a static image. We also wanted to include not only the map data, but the other data that shows walking patterns. And then because this is code-based rather than a bunch of images, if there was any tweak to the map design or the overall design, it was easy for me to do that and then just to give them the new code. So it's, 200 lines of code instead of thousands of images. So I did this by first taking the PostGIS database and exporting to a bunch of layers in a GPKG file. That included the geocoded home address, buffers around the home for visualization, the life log tables, and then that GPKG I zipped and put that on their SharePoint site. The interface you'll see in just a moment allows us to select, as I said, the subject, wave, and date. It gives the timestamp of the first and last step in the day. That gives us then the total duration of potential walking during the day. and then also graphs showing the walking patterns and distance to home. And then the map, leaflet map shows home, the home buffer, GPS, and walking intensity levels. So here you can see the difference between the two outputs. The one on the left is just a static map, and the one on the right is the Shiny application. And so those 2 days that I showed you before, one just shows the map, whereas the Shiny app shows a lot more information. And before I shift to the demo, I just wanted to acknowledge we wouldn't be able to do any of this work without the research subjects. They volunteer a lot of time and effort. Typically, they want to be involved in this stuff because it allows them to help other people with CP lead better lives through research. I'd like to acknowledge the PIs, the 3 staff people, Laura, Joel, and Neil at the 2 different centers, and of course taxpayers, National Institutes of Health, NIH, NICHD, through a specific grant number. I will reserve any comments about what's happening at the NIH now and go to the live demo. So you saw me load this up before. We were given permission by one of the families to show their data. So that's subject 36. And when I change the subject ID, then it allows me to select any one of the different measurement waves. And for each measurement wave, then it gives me the dates. So I'm going to collect one date, select one date, and I wonder if it's frozen because I switched out displays or something. So let's try this again. Back into RStudio. So just to give you a sense, it's really not a tremendous amount of code, and if anybody's interested later, contact me and I can share at least some of the code. Because this is reading out of this huge GPKG file with lots of layers, it takes a while to load up. There we go, okay. So this is showing each different measurement wave and the graph of walking over time. This is like the week that they were in measurement, and then they keep the device and then they bring it back to the study center. And so that's why you have this big gap of nothing, and then the day they bring it back to the research center, it looks like there's walking activity, but really it's just that week. And then we should be able to load different days. Okay. Okay, this is what it looks like. This used to be a really fast machine, but it's not anymore. But we can see the graphs. We have the graph of the number of steps across the time of the day and the distance to home and the map interface, which is a nice live, real, slippy map that shows the buffer of the distance to home. And that's it. I've done it within 20 minutes, and I'll take questions later since we're going to move on. Okay.